All right, thank you. If you want to pronounce it the French way, it's Martinot, but Martinot fine, it works fine. So hi everyone, thank you for joining us today. So sorry, is it Caleb? Yes, okay, thank you. As Caleb just introduced me, I'm going to present to you a particular aspect of the project that I've been working on. It's really focused on the, oh, sorry, just checking. Yes, good. Thank you. On how to combine both the moon mineralogy mapper data and the diviner data, because there are some problems that I'm going to get into just now. Okay, so from the samples brought back during the Apollo and Luna era, their study showed that there's three main minerals composing those rocks, and so plagioclase, olivine, and pyroxene. And so we can basically find most rocks falling in this ternary diagram here. But the rocks that we're interested here are the rocks that are in this red triangle here, composed of more than 90% plagioclase, which are called anorthosites. And they compose the lunar primary crust. And so the emergence of remote sensing surveys have allowed to map plagioclase exposures across the lunar crust. And in this study, particularly, we're interested in studying the variation of plagioclase within the anorthosites. And so we're doing, well, today I'm going to show some work to compare the M-cubed and diviner instruments. This is the map of selected craters. So outlined in colors, we see the major lunar terrains as defined by Jolliffe and collaborators. So in red, we have the South Pole Aitken terrain. In green, the Porcellarium crypt terrain. In blue here, the feldspathic highland terrain, which is the anorthositic part of that terrain. And then everything between the green and blue outline is the outer part of the feldspathic highland terrain. And so the craters here are, you know, across the lunar surface, and they're a little bit, they are located on all terrains. And we selected them based on the occurrence of previously detected pure crystalline plagioclase. Okay, so first of all, we make mosaics with the M-cubed or moon mineralogy mapper data. And we calculate a series of spectral parameters, which are shown here. So the integrated band depth, or IBD, at different wavelength ranges. So the IBD 1250 is calculating the integrated band depth or area of the absorption band in the red interval here. The IBD 1000 calculates the area of the band in the green region, and IBD 2000 calculates the band area in the blue region. And so after we calculate those spectral parameters, we are able to make color composites highlighting the mineral diversity of the lunar surface. And so the regions that we are interested in are the regions that are here in red. And I forgot to mention that this spectrum is a beautiful plagioclase spectrum. There is a single wide absorption band here. And those spectra that are in red here are good candidates for pure plagioclase, pure crystalline plagioclase detections. So after doing this, we manually check for the presence of this kind of that type of spectrum, and we map them out when they are present. And so this is just a close-up of the previous image. So this is Aitken crater, and the red polygons here are just the location of those pure crystalline plagioclase spectra. Oh, sorry. Okay, so after doing this, we move on to the diviner instrument data. And so diviner is a radiometer that is on board the beautiful Lunar Reconnaissance Orbiter. And the specific data that we're interested in from the diviner instrument is the CEF position that is calculated using the 3 thermal channels in the 8 micron region, because this CF or Christiansen feature, which is shown here in all of those spectra, is related to the mineral composition. And so I just want to attract your attention here on, so those are all different spectra, and this is albite and anorthite, so both plagioclase and members. And in this case, the CF varies according to the calcium content. And so what kind of distinguishes this study from previous studies that have used CF position maps is that it takes into account more observations, so hopefully we can have more precise CF maps. Okay, so we don't directly take the diviner data. We apply a bunch of filters in order to have the most stable data possible. And so, first of all, so I don't know if you're familiar with any of that, but one of the parameters that is within the pretty complex, there's a lot of steps in the diviner pipeline. One of them is the terrain discriminator. So this terrain discriminator is a value between 0 and 20 that will basically help calibrating or correcting the data to say, okay, this is Mary material or this is highland material. And so we fix it to 20, which is the value that is associated to highland terrain. We also use only data between the, in the lunar noon time that we call. So it's between 10 a.m. to 2 p.m. And I will show you a graph of that later. Another thing that we do is that we look at the emissivity spectrum and we look at its shape. And so here is an example of a V shape, which is a big no-no. We don't want that because that biases the resulting CF position. So we are filtering them out. And the last thing that we do is that we also filter out incidence angles that are superior to 60 degrees. And so here, for instance, on this graph on the bottom, all the blue points are data, early morning data. All the green points are late afternoon data, and then all the orange points are the noontime data. And what we can see is that, early morning and late afternoon data tends to have incidence angles at, more than 20, sorry, more than 60 degrees. I'm trying to stay professional, sorry. Okay. So there are a couple of problems when comparing M-cubed and diviner's data. One of those is that the M-cubed selenium location is not exactly perfect. So we had to manually reproject the data so that basically we're sure that we are looking at the same location at the surface between both data sets. So we redrew the locations that I showed you. So the red locations are the locations associated to the presence of pure crystalline plagioclase spectra. And in blue here are the corresponding diviner regions of interest. So it's a little bit smaller. Okay, so I told you that we only selected data between 10 a.m. and 2 p.m. And I think this graph shows, is a good representation of the variation of the Christiansen feature position as a function of time. So each point here represents 30 lunar minutes. And we can really see that there is a big scatter in the data. And those points are associated to the Humboldt central peak. And in blue here are the regions of interest where we find pure crystalline plagioclase spectra. And I just want to draw your attention on the fact that it's like a disco ball, right? We have regions of interest a little bit scattered all around the central peak. And this may cause those wide variations. Okay, so this is a summary of all the CF positions for all the craters that I showed you on the first map. And so they are kind of ranked by lunar terrain. And so in red, it's the South Pole Aitken terrain. In darker blue, it's the feldspathic highland terrain, the anorthositic part. Then in lighter blue, it's the outer part of this feldspathic highland terrain. And then in green, it's the Porcellarium creep terrain. And so, and the dashed lines here represent the terrain average. And so most CF positions are consistent between mature to immature to mature calcium-rich plagioclase. And we have higher values that are consistent with mixing between plagioclase and minor amounts of pyroxene. Those might be because of residual errors between M-cubed or during the M-cubed reprojection step. So all of this to really plug in the Lunar Trailblazer data. Really excited about that mission because we will not have problems with reprojecting data or all of that, and we will have better spectrally and spatially resolved data. So I'm really excited about that mission. And yes, all of this will be written up in an article coming up soon. Thank you for your attention.